Ah.
I mean, this is pretty solid.
Why don't you just throw something that you like to?
So no one has any particular questions?
What about isomorphism?
About, you want me to show you examples of isomorphisms?
But here you
That'd be good? All right. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day again. Thank you for this opportunity just to meet and study your creation. Just pray that you'd be glorified in what we do, Lord. In my prayer, Lord Jesus. Amen. So you want some examples of isomorphisms. Or Hilbert spaces. I'm not ready for Hilbert spaces. So isomorphisms. So you're looking for something like T, a mapping from a vector space V to a vector space W, both over the same field, right? And we need what? T is linear and bijective, right? So there are various strategies on how to find an isomorphism from one space to another. Like the question is how the space is characterized, I suppose. Example one, sometimes it's just kind of stupid. You could have V equals to R4 and W equals to R2 by 2. Right, like for me that's my notation for 2 by 2 matrices with real entries. And so you guys tell me what's the map? A, B, C, D. See, you guys don't, I mean, you already know this. Yeah, you don't need my help. Right? And, all right, does that, I mean, how do you know that's an isomorphism? Well, let's see here. How can we argue? First of all, you can check linearity. I won't waste your time on that. You guys, you do need to check that it's linear, right? And then let's see here. Is it onto? So it's clearly onto, right? If you have A, B, C, D in R2 by 2, right? Then T of A, B, C, D is equal to A, B, C, D, right? And maybe that's enough. Why would you already know that this is a one-to-one map then? Right? But we know the dimension of R4 is equal to the dimension of R2 by 2, which is equal to 4, thus T is 1-to-1. There's a theorem, right, that we should all know about, and the theorem is this. If the dimension of V is equal to the dimension of W, and T, a mapping from V to W, is linear, then T is onto if and only if T is injective. But be careful, you're only allowed to use this theorem in as much as you already know the dimension of your domain and your target are equal, right? If you don't know that, then you can't do this, and then points will be taken from you, sadly. Let's see here. Another example. What if we have like W equals to A in complex 2 by 2 space such that A transpose is equal to minus A. And then find N such that W is isomorphic to nth order degenerate polynomials over the reals. Right. So here, I'm viewing this as a real vector space, okay? I mean, obviously it's a set of complex matrices, but I'm going to keep it real. So how would you go about finding an isomorphism? What is PNR? Do you guys know? Is that the notation you guys use, or in AP Calculus? No? But this is something you study in AP Calculus, like for sure. This is the span of 1x, x squared, x to the power n. In other words, it's an nth order it's a set of all nth order polynomials possibly degenerate. In other words, I allow the leading coefficient to not be 0. It could be 0 rather. So technically speaking, if you have the leading coefficient be 0, then it's not technically an nth order polynomial. But anyway, who cares? So what n do I need to pick there? I don't know. So how do we come to terms with an example like this? So basically, the way I attack a problem like this is to try to understand what my W is, right? And I need to like look at an arbitrary element of it and come to terms with what its structure is. So to do that, I take an arbitrary element. It's a 2 by 2 matrix, right? So A is still A, B, C, D, right? And it's A transpose equals to minus A gives me what? That gives me D, B, transpose, right? C, B, A, and minus A, minus B, minus C, minus D, right? This is a 2 by 2 man, can I change it? No, I'm too far in. I won't change it. I'll let it be. It's not very complex. Anyway, so what do you got? You got D equals to minus A, and you've got B equals to minus C. That's kind of it, right? So apparently my arbitrary matrix looks like A, B minus A, I think. Wait a minute.
Wait,
I could be wrong. Tell me more.
Wouldn't A transpose be flipped over the main diagonal?
Did I not flip it?
I'm just like, why are A and B switched?
Oh, that's a good question. I don't know why I did that, but it's wrong, right? No, you're not. You're not crazy. You got to trust yourself. You got to speak up. So what would that change? Oh.
A lot.
Yeah.
Simplify things profusely.
A equals minus A, D equals minus D. I like those. So apparently it's just what? 0, 0, and yeah, so that's it. Yep. Now, these are complex numbers, right? So if I want to understand what this is as a real matrix, I can write this as like, let B equal to B1 plus IB2, right? And you'd have like B1, 0, 1, minus 1, 0, plus B2 times 0, I minus I0. So, in short, we see that W is the real span of these two matrices. Right? So apparently W is just a two-dimensional vector space. It looks kind of scary at the start, but it's just this. And that's its basis, right? Can you see how to prove? I mean, you can claim that this shows that those are a basis because it's clear that it spans the space by this calculation. And it's also clear that those are linearly independent over the reals, because if you set this equal to 0, it forces both B1 and B2 to be 0. Therefore, that's a linearly independent spanning set. It's a basis. And so if I want to just define an isomorphism, I can just do it as such, right? I don't like t for this example. I'm going to use psi. So I would do psi of 0, 1, minus 1, 0 is equal to 1. And psi of 0, I minus I0 is equal to x. And then I would extend linearly. See, if I define a mapping on a basis, if I map a basis to a basis, that suffices to define a linear mapping by the unique linear extension. That's a theorem we have, right? If I specify the values of a linear map on a basis, then there is a unique linear extension of that. Now, the formula for this is silly, right? It's just this, right? So psi of, how's it go? 0, B1 plus IB2 minus B1 minus IB2, that is just mapping to B1 plus B2x, which of course is an element of P1 over R. In short, the answer is that it's isomorphic to P1. So the funny thing about polynomials is the dimension is one more than the max degree, right? So like quadratic polynomials are actually three-dimensional, for instance. Any questions? Yeah.
How do you spell that Greek letter?
Oh, this? Psi, PSI.
So what would be the advantage of doing something like this? Obviously, it makes sense to translate it into R space because it's a lot easier to work with. But what kinds of ways would you, for example, like converting complex matrices into polynomials? Or is that more just a function of example?
Oh, I just making an example, but I mean, why would you do this sort of thing? Well, I'm kind of more interested. Let me show you what I'm interested in.
Sure.
So, what I'm interested in, among other things, is an isomorphism which does more than just this. I like isomorphisms which are actually algebra isomorphisms. So, like definition, a vector space over the reals, let's say, with a product star. So the product is it takes in pairs of algebra elements and it gives you back an algebra element such that. So here's the deal. First of all, there exists a 1 in A such that 1 sub A times x is equal to x for all x in A. So like there's a unity, all right? There's like something that behaves like the number of 1 in the algebra. The other properties of the algebra, I assume, is that if we've got like C is a real number, and if you have x, y, z in the algebra, then number 1, you have like cx plus y star z is equal to what you think it would be, and number 2, x star cy plus z is equal to what you think it would be. What do you think it would be? So you said c times x star z plus y star z. So in other words, what you're telling me is multiply like normal, you weirdo, right? Well, okay, I added the weirdo, but you know, I mean, this is. So what I'm saying right here is that the product has what's called bilinearity. It's linear in both slots, all right, and we can pull real constants out of it, all right. So that alone is just a kind of generic algebra. All right, but so you can study algebras in that sense. And the funny thing is some of you will soon take abstract algebra, right? And at no point will you be given a definition of algebra in abstract algebra. Because we don't study algebra in abstract algebra. We study groups, we study rings, and maybe in passing we might define an algebra. But the focus is not actually algebra. It's kind of a funny thing, the label. But so if in addition you have x star y star z is equal to x star y star z, if that makes sense, in the sense that this is equal to that, then A is associative. So associative algebras are nice, all right? It's an associative algebra. And if x star y is equal to y star x, and this is for all x and y and for all x, y, z, okay? Then A is commutative. It's a commutative algebra. So much more is known about associative algebras or commutative algebras, right? So can you guys tell me any examples of algebras? How about a non-associative algebra? Do you know any example of a non-associative algebra? Okay, just checking, make sure I put the camera in the right place. So a good example of that would be, we could just take V equals to like R3, right? And if you study the cross product, right? So like A cross B cross C, if you see that written in an engineering book somewhere, that means that the author doesn't know what they're writing. So you should throw that book out and find somebody who knows what they're doing. So no, the cross product is not associative, right? In fact, the cross product satisfies the following. It satisfies that this plus, oops, my bad. So that is the identity that the cross product satisfies. That is essentially describing how far from associative the cross product is. This is the so-called Jacobi identity. All right. And so essentially, if you have a vector space with a product which satisfies the Jacobi identity, it's called a Lie algebra. Well, there's a little bit more to it than that. A Lie algebra, satisfies Jacobi identity. There's more to say there. We usually use a different notation for Lie algebra. So like, this is the typical notation used for Lie algebra. Is usually the kind of notation that's used for Lie algebra, so-called bracket. Yeah.
For the Jacobi identity, would the result give you the bigger vector, or just?
Oh yeah, zero vector. My bad. So, yep. So, yeah, a Lie algebra is a vector space, and the Lie bracket, which I've written right here, is assumed to be bilinear. And it also has to satisfy the Jacobi identity, and it has other, more interesting things like AB is equal to what? Minus BA. So you can take a whole class just on Lie algebras, all right? There's lots of algebras which have the structure of a Lie algebra. But anyway, Lie algebras are a well-studied example of a non-associative algebra, all right? Okay, so what are other examples of algebras? How about this? What if we look at, I don't know what you guys' notation is for it, but I could look at linear transformations from a vector space to a vector space, right? Define, if I take, let's say, T star S, how would I define that? What would a product on mappings? So here, this is LVVs, like the set of all linear transformations from V to V.
Yeah.
How would you multiply two linear transformations? What would define an algebra product on those? So what you do is you do composition. See, because if you take the composition of two linear maps, you get a linear map, right? You guys have proved that. The composition of linear transformations is linear transformation. That's a mighty fine question for a final exam in linear algebra. I'm not sure that, I have no earthly idea what Dr. Skambordis is going to do, all right? But anyway, I'm just saying. But yes, you can check that is in fact bilinear, right? You can check it. It satisfies all these terms and conditions, and function composition's associative. So this gives an associative algebra. What's the identity? What's the number one? I gave it away. What's the number one in this algebra? The identity map, right? So id, if you like, id v of x is just equal to x for all x in v. Basically, the one in the algebra is the identity on v. That plays the role of the number one. If you want, you can make the set of linear transformations from V to V a Lie algebra. If you'd like to make it a Lie algebra, you can do that as well. You can do that by this. You define the Lie bracket of T and S to be T composed with S minus S composed with T. And you can prove that that actually defines the structure of a Lie bracket. Like, it's pretty clear that it's anti-commutative. It's got this snazzy product down here. And it is a straightforward but tedious calculation to show it satisfies the Jacobi identity. So this is a rather well-known example of a Lie algebra. But the truth of the matter is, any associative algebra you have, you can define a Lie bracket like this. You just take xy, and you do x star y minus y star x. So this right here is the Lie algebra induced from an associative algebra product. So anytime you have an associative algebra, you can induce a Lie algebra by using this so-called commutator bracket. This is a general construction. What's another example of an algebra that's interesting that you guys have seen actually? Another example of an associative algebra that you've seen would be, how about n by n matrices over a field? What's the product? If I have two matrices and I want to multiply them, according to some algebra product, what should I use for my product? You guys have had 221, right? You remember with nostalgia 221, when everything made sense. It was all nice and tidy and concrete in the world before proofs. AB, the product of matrices, the matrix product, is satisfying all of these terms and conditions. It's associative. What is the unity in this algebra? It's just what? The identity matrix, right? That's what serves as the number one here. So, all right, now that you guys have a taste of it, this is what an algebra is, all right? It's an abstract set paired with a multiplication that's bilinear. And I like to look at ones that have a unity. I can give you a slightly more abstract example. Actually, it's not that abstract. So you guys want me to talk about complex? Well, here it is. A equals to the complex numbers, z times w. In other words, x plus iy times a plus ib. Define it xa minus yb plus I times xb plus ya. Complex multiplication defines an algebra. The complex numbers are an algebra. Of course, you'll learn towards the end of next semester, I guess. Well, actually, we're already talking about it in here, right? What's a field? Yeah? The formal study of field theory happens at like the end of 421, maybe. But yeah, what's a field?
Doesn't it satisfy axioms of some sort?
Axioms of some sort, yes, I agree. How would you describe why is example 6 a field, whereas example 4 and example 5 and example 3, none of these are fields? What makes a field a field?
Well, so a field has to be associative and commutative.
A field has to be associative and commutative. Very good. Commutative, that's good. So fair enough. That rule, commutative rules out. You got me right there. These are all not commutative. Fair enough. Man.
They also need to have an additive identity and a multiplicative identity, if I remember correctly. They also need to be closed.
Right.
Is it related to like the homomorphism?
Yeah, so right, a field is, it's a set which has an addition, a multiplication, and those addition and multiplication interface in the usual way, right? Like you've got distributive properties that intertwine the multiplication and the addition in the natural way. Addition meaning that the set is closed under the operation of addition under inverses, right? Every element has an additive inverse. There's a 0 in the set such that 0 plus anything is the anything. There's a 1 in the set such that 1 times anything in the set is the anything again. And here's the sticking point. Every non-zero element in the field has to have a multiplicative inverse. That's what makes a field a field. So this is a little bit off topic here for my current discussion, but just to bring a little bit of nuance to it. Z, not a field, but the rational numbers are a field. See, because like 2 inverse is 1/2, right? Which is not an element of Z. Whereas, well, P over Q inverse is, well, here you go, Q over P, you're welcome. So like inverting, finding the multiplicative inverse of a rational number is as easy as flipping the numerator and denominator. That's easy. Finding the inverse in the algebras we're about to look at is far more nuanced. You guys know that already. For like matrices, right? Finding the inverse matrix is a pain, yeah? Okay, so what does it mean for two algebras to be isomorphic? What is that? So if you had A1, you'd say it's isomorphic to A2 if and only if there exists like a bijection psi, let's say from A1 to A2. And what do you think, what properties should psi have? So the concept of isomorphism is more general than the class you're currently in, all right? Like the concept of isomorphism is that an isomorphism should preserve the structure of whatever you're looking at. Yeah, so it's always a bijection. That's just set theory, right? But more than that, it has to preserve the structure. So like for here, one thing we need is linear because there's an additive structure we want to preserve. And that's it for you, right? For vector spaces, it's an isomorphism if it's a bijection, which is also linear. That's all you guys are doing is vector spaces. That only structure you have to preserve is the additive structure. But for for an algebra, there's more. We also need to, I'd also kind of like to map 1 to 1. So the 1, in other words, the 1 for A1, I'd like it to map to the 1 for A2, okay? That's not the 1-to-1 property, although it is kind of the 1-to-1 property. But that's just a pun. Not a very good one. No, I stand by it. I apologize for nothing. And then also, you'd like the product to be preserved. So like, if I have A star B, I'd like that to be psi of A star psi of B. And of course, this
So
is...
stars don't have to be the same.
Yeah, to be clear, let me maybe call this a star sub 1 and a star sub 2, all right? So, all right. Some really neat stuff happens in the case that our algebra is a copy of like Rn. We're able to find an isomorphism into the set of matrices. So like example 8, if I think of the complex numbers as R2, all right? Let's see here. Oh. Sorry, I'm a little rusty. I'm thinking of something. Oh. Well, maybe we can derive it. I think that this should be isomorphic to some set of like matrices that are like complex numbers, which are a subset of R2 by 2. All right? So let's see if we can derive this set of matrices from the criterions that I've written down.
When you say that the complex numbers equals R2, you're just saying that those are two-dimensional. Right?
Yeah, I'm just saying that I'm really just proposing that A plus IB is notation for AB.
All right.
So really what this is saying is that E1 is 1 and E2 is I. That's the specific implementation. But, okay, so we're looking for an isomorphism, right? So like psi of A plus IB is equal to some kind of matrix over here, right? well, it's equal to some matrix in 2 by 2 matrix. So I guess I can just call that, CD, for lack of imagination, CDEF, I guess. What should I put here? How does it work? Right? So think about this. Because, look at what psi is. Psi is a mapping from R2 to, R2 by 2, I guess. Oh, see, that's still not quite the right setup, guys. I'm sorry. Well, let me set aside my fears and just calculate here. So,
we're mapping into a 2 by 2 matrix. That has up to 4 dimensions, though, right?
that is true. Yes. So, but we know some things, right? We know that psi of 1 had better be equal to 1, 0, 0, 1, right? And we also know that psi is a linear map, right? So I claim that that means that, well, let me not, I'm sorry, I've come at this from a weird angle, so it's messing with my head. But that must actually be true.
Yeah.
And we also know that like psi of A should be A times psi of 1, right? So we know that. That starts to feel like a thing. Let's see here. We also know that psi of II is equal to psi of minus 1. So that tells me that psi of I times psi of I is equal to minus 1, 0, 0, minus 1. So if I stick with my generic, to be clear, the C, the D, the E, and the F, they're all functions of A and B in this way of thinking. I know what the answer is, but that doesn't, I don't want to just write it down. Man, this is really hard the way I'm coming at this.
Would you, if you were writing it in terms of A and B, instead of C, D, E, F is A and B, would you kind of rewrite it in a way to show that, so if you had psi of A plus IV equals A of the matrix be A, B, negative B, A, and then you show that it's 1 to 1 and on to, and then you show only B. Would that hypothetically work?
Well, I'm assuming that it's 1 to 1 and on to.
Oh, you're already
I mean,
assuming that. You don't have
yeah, I'm trying to show. I'm assuming that, suppose you have an isomorphism.
Okay.
I'm assuming we have an isomorphism, and now I'm trying to derive what it has to be.
Oh,
Yeah.
Okay, you're working back. I see. That's interesting.
Right. So I've been very cagey with you guys. I didn't tell you what the M sub C was. We'll find that out in the process of this derivation or not, because I'm going to get stuck. All right? Yeah? Preston already knows the answer. He's not really allowed to say anything. Go on, yeah?
I don't know the answer.
Oh, that's not good.
And I should know the answer.
Yeah.
But,
Actually, you should know the answer too.
Me?
Yeah.
No.
No.
For what C, D, E, and F?
Mm-hmm.
A and B?
Yeah.
Okay, I see what you mean.
yeah, but it seems like we should get D and E equaling 0 if we have a bijection given the dimension. Is that wrong? What did I say? C and D, D and E? Is it meant D and E, whatever I said.
Well, I'm sorry. So let me. Sorry, Preston. I'm not tracking yet. CD. We have a CDEF times CDEF, right? That's supposed to be equal to what? Minus 1, 0, 0, minus 1. That might tell us something. I don't know. So we get, C squared plus DE equals to minus 1, and good grief, yeah. What you got? CE plus what? FE equal to 0, and DC plus DF. That can't be right. Oh, DC plus DF equal to 0, and I regret this. DE plus F squared equals to minus 1. What does that tell us? Anything? Oh, that tells C squared is equal to F squared? Yes. C squared equals to F squared. I like that. That's a thing. So that tells us that F is equal to plus or minus C. Right? And then
F is equal to minus.
we've got, did I make any mistakes in the multiplication? If I did, let me know. So this,
CE plus FE is 0.
So that's C plus F times E equals to 0, right?
So, so either E is 0 or F is equal to negative C.
And likewise, what do we got?
Down there we have CF times D is 0.
Oh, so apparently, we better have, I think we're going to have C plus F equal to 0. Otherwise, it's going to force both E and D to be 0, which will get us into trouble when we work through it. Because if C and D are both 0, that contradicts this equation.
Because C squared is equal to negative 1.
Aha. So,
And B's, wait, does the matrix have to have real entries?
therefore, yes. So therefore, because I said so. So C has to be equal to minus F then.
Yeah.
C equal to F or minus F?
It has to be minus F.
I thought you said C plus F is 0.
C plus F is minus, C plus F has to be 0, I think.
Okay.
Either be negative F plus
Oh, yeah.
I don't want that. That ain't right. Man, what the what?
But yeah, we don't have that anyway, because
Uh,
1, or psi of 1 can be F1.
huh. I wanted C to be equal to F, honestly, guys. So I don't know what I did. It's something screwy.
Oh, we should have C squared minus F squared.
Oh, really?
Because if we,
Yeah.
well,
If we add
If
C
we-
squared plus BD,
C squared minus F squared equals, oh, no, because we're still going to get C squared equals F squared. Fine.
Oh, I'm a dummy. So let's see here. If C is equal to minus F, what else do we have? We have I'm sorry, I'm thinking about this problem wrong. Let me show you guys. Man. Well, the answer here, and I was really hoping we'd be able to derive it, but obviously I don't know what I've done. The answer here, which I really was trying not to just pull out of thin air, is A, there are various ways you could do it, B minus B, A, like that. That matrix, you can prove that that is an isomorphism. I'm going to erase the evidence. Oh, man. I don't know. There's something wrong about the way I was thinking about it just now, guys. I'm sorry. But you can check, though, that this actually satisfies the property like psi of z times w is equal to like psi of z times psi of w. All right? And obviously, like psi of 1 is 1, 0, 0, 1. And psi of I, all right, is equal to like 0, minus 1, 1, 0. And you can try it out. This matrix, come on, this matrix, getting trapped, is a matrix whose square is minus the identity. So this matrix is like the number I in the set of 2 by 2 matrices. So this particular two-dimensional subset of the 2 by 2 real matrices serves as a version of the complex numbers. So let me show you the calculation I was hoping we would get to for my final example. Ah, man. Well, this won't take long. So example 9, if my algebra has the form like it's x plus jy plus j squared z, such that j cubed is equal to 1, and then proceed normally. So this is a three-dimensional algebra, And it's, have any of you guys had like number theory? Nobody? Okay. So here j cubed is equal to 1. This is a weird, and j is not a real number, okay? So this is essentially a three-dimensional algebra. And so check this out. If I do x, well, let's say a plus jb plus j squared c times x plus jy plus j squared z. If I calculate this product, what do I get? I get ax, j times j squared is 1, so plus bz, and j squared times j is 1 plus cy, all right, plus j, let's see here, so a times y, b times x, and j squared times j squared is what? J to the fourth, which is? J. So I get plus this cz term, and then finally plus j squared. I get az plus b times y plus c times x. All right? And let me rewrite that in like column vector notation so we can see we're doing better. So we've got ax plus cy plus bz. We've got bx plus ay plus cz. We've got cx plus by plus az. And you guys can write this as a matrix column product, yes? So this is the matrix A, C, B, B, A, C, C, B, A. This right here is basically psi of A plus JB plus J squared C, all right? So this is a sneaky way you can find an isomorphism from a given algebra into the set of matrices of the same dimension as the algebra. This is a three-dimensional algebra. This matrix is going to actually give me a way to map into 3x3 matrices, and there'll be an algebra, like A is isomorphic to the set of matrices of this form, which is a subset of our 3x3. Now, you're right, 3x3 is a 9-dimensional space. This is very wasteful in some sense, right? This is a set of all such things is a 3-dimensional subset of this 9-dimensional space, but it also forms what's called the regular representation of the algebra. So the regular representation of the algebra is formed by taking the standard matrix of the left multiplication maps in the algebra. That's what this is. This is left multiplication by A plus JB plus J squared C on X plus JY plus J squared Z. Anyway, if I had thought of this before that last example, we would have been able to derive the thing I pulled from the thin blue air by looking at this kind of calculation for the matrix case. But anyway, I teach this stuff in complex analysis when I teach it because actually this is the right way to understand complex analysis in terms of complex analysis is one example of a much larger, broader idea of hypercomplex analysis where you can talk about how to do calculus over such an algebra. And in short, the way that's done is to assume that when you differentiate the Jacobian matrix of such a map, it has to be one of these kind of things. That's what it means to be differentiable of an algebra, is for the Jacobian matrix to have the form of the regular representation. Anyway, this will not help you with your final. But hey, I asked you guys for questions, and so it's not my fault. I was going to solve your homework problems, but